This is lesson 10.2, day 1. The learning targets for this lesson are that you can find the nth term of an arithmetic means of arithmetic means of arithmetic sequences, and you can find sums of n terms in arithmetic series. So our focus is arithmetic sequences in series. And by arithmetic, we mean linear. So an arithmetic sequence, like a linear function, has a constant difference between its terms. And we should probably actually articulate that a little further by saying a first constant difference between its terms. It's also called the common difference. The notation for the common difference is d. To get d, the common difference, subtract a term from its succeeding term or its previous term. Not the position, but the value itself. Determining the common difference. Determine the common difference, example 1, and find the next 4 terms in each arithmetic sequence. Well, negative 67. Some of us already see the pattern, that's great. Negative 67 minus negative 98. Negative 98 minus negative 129. We get a common difference of 31. So the common difference is 31. All I'm going to do is continue subtracting 31 from these values. Or actually adding 31. So I'm going to do negative 67 plus 31, which gives me negative 36, plus 31, negative 5, plus 31, 26, plus 31, 57. So we're using the recursive pattern, like how do we get from one to the next? And that's just d, by adding the value of d. So we'll talk about writing algebra rules in a second, both the recursive and explicit. For the next one, 130 minus 187 is negative 57. 187 minus 244 is negative 57. So in this case, our common difference is negative 57. We just take our previous term and add negative 57 to it to get the next term. Oh, sorry, minus 57. 16 minus 57, negative 41. I should just be able to hit enter and I should continue doing this. Negative 98. So there are our next 4 terms. The nth term of an arithmetic sequence. The explicit rule to find the nth term. The explicit rule to find the nth term is a sub n, which is the output of the nth term, is equivalent to a sub 1 plus d times n minus 1. Some of you see the similarities between this and a linear equation. This is y, that's our output. X is our input. We have our slope here. And this is the initial value. It's not really our y-intercept, though, unless we distribute d and combine that with a sub 1. But we don't have any exponents or any fractions that involve the value n, so this is a linear equation. That's the explicit rule. The recursive rule, which you may have already guessed, recursive, is taking the previous term and adding the value of d to it to get the next. So a sub n equals a sub n minus 1 plus d, and you'd have to give a value for the first term, a sub 1. We don't know this because we don't have a specific rule that we're doing this for. So for example 2, find both the explicit and recursive formula for the nth term of each arithmetic sequence. Well, first we have to find the value of d. In either case, we have to find the value of d. So negative 19 minus negative 36. And we're going to get to some that are not that are not arithmetic. So I like to check all the numbers to make sure they do in fact have a common difference first. Because if they don't, then I can't use this arithmetic formula for the explicit rule or for the recursive rule. I'd have to use something else. So for this one, D is 17. That means that our recursive rule will be a sub n equals a sub n minus 1 plus 17, where a sub 1 is negative 53. There's our recursive rule. For our explicit rule, we'll have a sub n equals the first term, negative 51, plus our common difference of 17 times n minus 1, just like we have up here. First term's value plus the common difference times n minus 1. We can simplify this further. It would be a sub n equals, this would be 17n minus 17. And when you combine the negative 51 and the negative 17, you get negative 34. It would actually be 17n minus 34. And so here it looks even more like a linear equation because we have the slope of the equation, and which is the common difference, and the y-intercept. The y-intercept is not the same as the initial value, though. All right, if you can, take a moment to pause the video and try letter B. Welcome back. If you did this correctly, you should have gotten a D value of negative 8, that your recursive rule would be a sub n equals a sub n minus 1 plus negative 8, or minus 8 if you want, and that your explicit rule was a sub n equals 25 plus negative 8 by n minus 1, which would give you negative 8n plus 33. For letter A, an example 3, the common difference, find the 38th term of the arithmetic sequence. So when they say arithmetic sequence, we know we're not adding the terms. When they say find the term and we know arithmetic sequence, we know we first need to find the explicit rule. Or if you want, you could do this till you get to the 38th term, use the recursive. I would not recommend it, but you could. Find the 30th term of the arithmetic sequence. So 25 minus negative 2 is 27. Negative 2 minus 29 is also 27. So our common difference is 27. This makes our arithmetic rule a sub n equals negative 29, our first term, plus d, which in this case is 27, times n minus 1. This is our first term. By the way, the 1 represents the first position. Technically, I could have changed this to a sub, this to a sub 2, and that to n minus 2. This is position 1, just like n is the term number we're looking for. This is term 1, position 1. This is its actual term value, a sub 1. So when I go to find this, because I want to find the 38th term, I'm still going to use my negative 29, which is my first term, plus 27, but I want this for term 38, so that means that n is 38. And since this is the first position, I'm going to subtract 1 from it. I plug this in all at once if I want to. Negative 29 plus 27 by 38 minus 1 gives me an answer for a sub 38 of 970. Now in the next one, they actually want us to find the value of d. It's a little bit different, but it goes back to this same explicit rule. If they don't give us the sequence, then I can't calculate the value of d by using the subtraction of the previous term. I'm actually going to have to plug these in the formula. I know a sub 38, so here's what I have. A sub n equals a sub 1 plus d times n minus 1. Now, if they don't give me the first term, if they give me, let's say, the second term, then I'd put a 2 here. Or if they give me the third term, if they told me a sub 3 equals 75, I'd put that number here and put a 3 here. But in this case, they do give us a sub 1, which is 75. They do not give us the common difference. That's what we're trying to find. We also know that the value that other value they gave us was 56.5. That's the a sub 38. So this would be position 38 associated with this term, just like position n is associated with this term. And this would be minus 1, position 1, associated with the first term. So all I did was plug in a sub 1 here with my position 1, a sub 38 with position 38 here. So now I can subtract 75, 56.5 minus 75. Actually, before I do that, I'm actually going to distribute d. We'll actually subtract this. It's 37, so I have 56.5 equals 75 plus 37d. So I'm going to subtract 75 from both sides, giving me negative 18.5 equals 37d. And then I will divide by 37, which gives me negative 0.5. So the value of d is negative 1/2, or negative 0.5. Example 3c, related to finding the nth term, again related to using the explicit formula for an arithmetic sequence. Find the first term of the arithmetic sequence. This time they don't give me the first term. They give me the 44th term, and they actually give me the value of 8. So in this particular case, I have, again, I start with the arithmetic explicit rule, a sub n equals a sub 1 plus d times n minus 1. Well, they told me the value of d, so that's helpful. And I'm trying to find a sub 1, so I'm going to leave that in my formula. My a sub n, though, is the 44th term, so I'm going to make this 44 minus 1, and its value is 229. So the value of the 44th term goes here, and the position goes here. Now I just have to do 8 times 43, which is 344, and subtract that value from 229. Which gives me negative 115. So we found the first term. From here, they could actually ask us, they actually could have given us this problem and said, find the 36th term. Well, you can decide, are you going to go backwards till you get to the 36th term, or are you going to find this? Well, there's more we could do with that, but are you going to, if you find this, you have the general rule, you could find the 36th term. Arithmetic means. The terms between two non-consecutive terms in an arithmetic sequence are called the arithmetic means. The arithmetic means are the terms between two non-consecutive terms in an arithmetic sequence. So really, we're looking at, we have a few numbers, and then we have some spaces. So we had a number here, and then we have some spaces. We don't know how many in a number here. What we are going to do is kind of try to use the recursive pattern, sort of. We're going to use the recursive, once we know this, we just keep adding the value of d to find those terms. But we have to calculate the value of d first. So we'll probably use an explicit formula to find the value of d. And then once we have that value of d, you can either do the explicit rule to find each term, or you can use the recursive to just add d to each previous term. You should end up back at this number. Always check that you do. So write an arithmetic sequence that has 5 arithmetic means between 6.2 and negative 1.6. 6.2, 1, 2, 3, 4, 5 spaces, negative 1.6. Now, I don't know where they fit in the sequence, but for our purposes, I'm going to pretend that this is a sub 1, and that makes this 2, 3, 4, 5, 6, 7, a sub 7. Using the explicit rule, I can find the value of d. So I will have my negative 1.6 being my 7th term equals my first term plus d times n minus 1, in this case, position 7 minus position 1. So I have negative 1.6 equals 6.2 plus 6d. From my negative 1.6, I'm going to subtract 6.2 and divide by 6, giving me a value of d of negative 1.3. So now I can add negative 1.3, or rather subtract 1.3 from 6.2. And this pattern should work all the way across. So 6.2 minus 1.3. And I do it again. Oh, wait. Minus 1.3. So I have 4.9, 3.6. Now I can just hit enter. It'll continue the pattern. 2.3, 1, negative 0.3, and negative 1.6, ending right back where we expected to end. So that way we know we calculated the correct value of d. Please take a moment to pause the video and try letter B. Welcome back. Write in the sequence that has the 6 terms between 12.4, 1, 2, 3, 4, 5, 6, and negative 24.7. So yes, we do expect d to be a negative value. If you did this correctly, you should have gotten a value of d, I believe, of negative 5.3. To set that up, you would have had negative 24.7 equals 12.4 plus d times, this is the 1, 2, 3, 4, 5, 6, 7, 8th position, so 8 minus the first position, 1. And you would have solved for d. Following this pattern, 12.4 minus 5.3 would give you 7.1 minus 5.3 gives us 1.8, negative 3.5, oops, oh, sorry, minus 5.3, minus 5.3, negative 8.8, negative 14.1, and negative 19.4, but don't stop there. Make sure that you found the right value of d by hitting it one more time, negative 24.7. So here are our 6 answers for the 6 arithmetic means between those two values. First difference versus second difference. First difference is like the common difference. We subtract each term from its successive or previous term. And if we get the same number, then we know it's a linear function, or if it's a sequence, an arithmetic sequence. Same value, which we call d if it's an arithmetic sequence. If it's not if it's actually points, an x and y coordinate, then we would call it m, the slope. So that would be the value of d. So this would be a linear function or arithmetic sequence, the arithmetic sequence being represented by a linear explicit rule. And we've had several examples of this. That's what we've been doing this entire note so far. However, if during the first difference we don't get the same value, one of the things we can do is test to see if we have a quadratic equation. And that would be if they have a second common difference. And if they don't, then we could test for a third common difference, which would be cubic, and so on and so forth. We could also test for logarithmic, doing other things other than common differences. It would actually be common quotients. But we'll get to that later. You should have hopefully gotten to that in Algebra 2. So anyhow, we have, if we subtract each first term and we have here's where we subtract each first difference from the previous one. And what happens is, if we get the same number, then we have a quadratic. Quadratic. And we can actually either figure out the equation or use our technology to help us calculate the equation. But it would be something like a sub n equals a sub n squared plus b sub n, or a n squared plus b times n plus c. Just like y equals x squared plus b times x plus c for any quadratic equation. So let's take a look at this. We're supposed to find a quadratic model for the sequence, or see if we can figure one out. There's actually a rule to do this, and you'll see, we'll summarize the rule in just a second. What we're going to do is we're going to do actually this is a sub n. So let's take a look at this. We've got this sequence. And we're thinking at first, when we go to do a quiz problem or a test problem, that, oh, it might be arithmetic. Let me take the first common difference. 36 minus 22 is 14. 22 minus 10 is 12. 10 minus 0 is 10. 8 and 6. There's our first differences. They're not the same, so we do not have a common difference. It is not a linear or arithmetic sequence. And then if I take the second differences, I get 2's for all of these. Because during the second difference I got 2's, I know that this will be quadratic. It's not going to be arithmetic or linear. It's going to be a quadratic equation. Well, there's a rule that we follow, and it is that we actually, this is times n, we actually put in the first term here with the first term's value, the second term with the second term's value, and the third term, put a 3 here and here, with the third term's value, and we can actually solve from there using a system of equations. So we have our first, so what I'm going to do is, remember, a sub n equals a times n squared plus b times n plus c. So I'm going to do this for the first 3 terms. For the first term, its output, wow, oh, I'm looking at the wrong problem. Its output is negative 14, and so that's going to be a times 1 squared plus b times 1 plus c. And for our second one, we have an output of negative 8, and that's for a times 2 squared plus b times 2 plus c. And for our third position, we have an output of 0, a term of 0, and that's a times 3 squared plus b times 3 plus c. So in terms of our system of equations, I have the following. Negative 14 equals 1a plus 1b plus 1c, or a plus b plus c. In terms of our second equation, I actually have negative 8 equals 4a plus 2b plus c. And by the way, if it's always the first, second, and third term, it may not always be, but if those are the values that you can use and pool, they're probably the easier ones. It's not as easy to pool the fourth, fifth, and sixth. Then you'll always have 1, 1, 1, 4, 2, 1, and you may have guessed it, 9, 3, 1, because 3 squared and 3. So 3 squared times a, 3 times b, and then our c. And that was an output of 0. So now it's up for us to solve this this system of equations to find the values of a, b, and c. Pause the video for a moment and give that a try. So you do need to remember how to solve systems of equations, which we did actually first semester. And you could do this system without a calculator. But we're going to do this using matrices. You're going, oh no, matrices. I've showed you how to use it with your tech for those of you who watch the video. So if you want to do it by matrices, that's how I'm going to choose to do it. I'm going to enter a 3 rows by 4 columns. But I have to reverse this. I have to remember to put these as my last numbers. So I have 1, 1, 1, negative 14, 4, 2, 1, negative 8, 9, 3, 1, 0. So now that I've done that, I can actually go to matrix A, but this time, so that's my matrix. I have this whole system entered as a matrix with my constants on the right side of the augmented matrix. And I'm going to go do row reduced echelon form of matrix A. Whoops, I don't want to be in the matrix when I do that though. Row reduced echelon form of matrix A. And so that gives me that my value of A is 1, my value of B is 3, and C equals negative 18. So I'm not going to, even though I do still need to know how to solve this algebraically using linear or Gauss-Jordan, if you wanted to do matrices by hand, I'm going to let the technology do some of the computational work for me so that I can focus on other things. So we did this by matrices. So our equation for the explicit rule for this particular sequence is a sub n equals 1, remember it's an squared plus bn plus c is our equation, but we have to know the values of a, b, and c. So a sub n equals 1 times n squared plus 3 times n minus 18. And if I put this in my calculator into the y equals x squared plus 3x minus 18, and I go to my table, I should see this exact sequence, negative 14, negative 8, 0, 10, 22, 36, if I have 1 through 6 entered in there. And I do, so I know that I have the correct explicit rule because for each position, 1 through 6, I had these terms. Take a moment to pause the video and try this for letter B. If you do this correctly for letter B, then you got the first common difference of 5, 7, 9, 11, and 13. Second common difference of 2. So again, a quadratic formula. So we set up our system. We have the first term being 0 equals A plus B plus C. The second term being 5 equals 25A plus 5B plus C. The third one being 12 equals 3 squared, or sorry, that's position 2, not 5. This should be a 4A plus 2B, because it was position 2. Position 2 squared is 4. Position 2 times B is 2, so this would be 4A plus 2B plus C. This should be 9A plus 3B plus C. So here's our system written as an augmented matrix to save myself from doing the elimination, which I could do, but I don't feel like it. I'm going to write an augmented matrix. This is 9, 3, 1, and then this would be 0, 5, and 12. So now I'm going to put my augmented matrix into the calculator. So I go to Matrix, Edit, and what do you know? Because we did quadratics last time, I have the first 3 columns all set. I just have to change the constant. That one's 0, this one is 5, and this last one is 12. And then I quit that and I do matrix. I want to do row reduced echelon form, Gauss-Jordan, aka Gauss-Jordan, of matrix A, gives me that A is 1, B is 2, and C is negative 3. So our equation, A sub n equals n squared plus 2n minus 3. We can, again, double check that by putting the explicit rule into the calculator, x squared plus 2x minus 3, going to our table, and we should see for inputs of 1 through 6, the position 1 through 6, outputs of 0, 5, 12, 21, 32, and 45. This concludes today's day 1 10.2 notes. What we looked at was how to find the explicit rule for a quadratic sequence, how to find the arithmetic means, and how to find specific values using either the recursive or the explicit rule for an arithmetic sequence. Your assignment that goes along with this part of 10.2 notes is for day 1, we're looking at page 605, 1 through 37 odd. Have a great day.